So let's make a recap about the previous laboratory in the course 2. It's about it teaches one of the three major ideas in deep learning, which is the learning rate or hyperparameter tuning, model evaluation metrics like accuracy, precision, recall, and F1. And last is batch size tuning. The model use is a CNN trained on CIFAR 10 images. So let's begin in the import and setups. The notebook that we have used is first import the libraries needed like the pandas, torque, torch NN, torques NN that functional, torch that omnin. Pandas is the purpose is to organize the experiment results for data manipulation, like that, organize experiment results. Torque for PyTorch library, torques.nn, the neural networks layers, torque.nn.functional activation functions, torque.optim, optimizers like SGD or Adam. So and then we select what the device we're going to use. It's either CPU or GPU or CUDA. If GPU exists, it will prompt us as CUDA, and otherwise it is CPU. Why this matter? Because training deep learning models is much faster on GPU. That's why we use CUDA. The model is simple CNN. The notebook defines a convolutional neural network. Um, CNN are commonly used for image recognition. CNN pipeline is from the image. After the image is convolution. Other convolution is activation. Where the activation is pooling, and after the pooling is fully connected, then output. The CNN detects patterns such as layer that's in the early. It detects the edges in the early layers. In the middle layer, it's now can detect the texture patterns. That it's only the detection, not having an output. And the deeper layer is already the shapes. And then finally, the final layer, it could tell us what object it is. No, it didn't, but the pattern objects. We could detect them. This connects to what we were asking earlier about the feature detection in neural networks. So, next is training function. The notebook defines function. This function does three things. Um, this training function train, evaluate, and we could put the learning rate. One, create the model. Next is train the model, evaluate the model. Step one, we should have model creation. Is equivalent to model is equivalent to simple CNN that to device. Model creation. We define the model and the neural network we're going to use and define the device. This create the CNN moves to GPU or CPU. Step 2 is optimizer with learning rate. So we define the optimizer together with the learning rate, like optim.adam model the parameters, and inside of it is learning rate. Optimizer updates the weights using gradient descent. Okay, the optimizer updates the weights using gradient descent. The important hyperparameter here is learning rate. So what is learning rate? Learning rate controls how big the weight updates are during training. So the formula of gradient descent is weight is equivalent to weight, the new weight is equivalent to old weight minus learning rate multiplied by the the change of loss with respect to W. So symbol, W means weight, L is loss, A is a learning rate. I think the symbol is not the A, alpha or theta. If learning rate is too small, training becomes very slow. Like example, 0.001. If learning rate is too large, training becomes unstable. Example, the model will never converge. So the good learning rate, the notebook tests several learning rate. They train 0.001, 0.001 until we have to the point to 0.1. Next is plotting results. The results are plotted, learning rate versus accuracy. So typical outcome, if we have a learning rate, we set the hyperparameter learning rate is equivalent to 0.0001, the accuracy is low. And if this 0.001 is better, and 0.001 is the best, and above that is worse, terrible. So the best learning rate lies between the low and the high um, learning rate. So in the middle of it, we could found the best learning rate. So the conclusion is 0.001 is the optimal learning rate. Model evaluation metrics. The notebook then teaches evaluation metrics. Many beginners only look at accuracy, but that's not always enough. Metrics involve accuracy, precision, recall, F1 score. Next, accuracy. Accuracy measures how many predictions are correct. So the formula of the accuracy is correct prediction divided by total prediction. So, for example, we have the 2 correct and 3 total. Out of 3 total, only 2 are correct. So the accuracy is 0.66. Let's talk about the precision. Precision answers when the model predicts a class. How often is it correct? Okay, precision means when the model predicts a class, how often is it correct? So typically, the formula of precision is true positive divided by true positive plus false positive. Like for example, model predicts cat 10 times, but only 7 are real cats. So the precision is equivalent to 7 over 10.7. The model predicts cat 10 times, but there are 7 are real cats. There are 3 wrong, so false positive. There are 3 false positive. Talk about the recall. Recall answers how many real objects did we correctly detect. So the recall formula is equivalent to true positive divided by true positive plus false negative. Like for example, there are 20 cats in the data set. Model detected 10. It's only detected 10 out of 20. So the recall is 0.10. F1 score. F1 balances precision and recall. So the formula is equivalent to F1. It's equivalent to 2 times inside of the parenthesis, the circular parenthesis is precision times recall divided by precision plus recall. It is used when the data set is imbalanced. Like for example, we have the precision, which is a value of 0.8, and a recall, which the value is of 0.6. So the F1 is 0.685. So let's talk about the implementing metrics in PyTorch. We use the evaluate underscore metrics parenthesis used inside the text metrics. Let's talk about micro versus macro. Micro average means reach all predictions equally, used for accuracy. When you talk about macro average, computes metric per class that averages, used for precision, recall, F1. Let's talk about metric evaluation loop. During evaluation, we have for images, labels. For images, we talk about labels in the data loader. So steps is forward pass, get prediction, update metrics. Example, uh, threads, prediction, secret torques that args max outputs, and comma dim equal 1. This selects the class with highest probability. Expected output, the notebook shows something like accuracy, precision, recall, F1 scripts value. Low values happen because model is not trained long enough. So, what's the difference with metrics and learning rate? Metrics versus learning rate. The Dodo trains models again for different learning rates. For each learning rate, it records accuracy, precision, recall, then stores results in the metrics. Converting to data frame, like Pandas data frame, this allows us for easy visualization. Next is batch size tuning. The final section explores another hyperparameter, batch size. Batch size means how many samples are processed before updating weights. Like for example, we have the dataset as 10,000 and batch size as 100. Then 100 samples update weights. Means update weights. Small batch examples 32. So the pros, more accurate gradient, better generalization because slower training. Large batch example is equivalent to 512. The pros is faster, but the cons is worse generalization. Key lesson here is model hyperparameter depends heavily on, model performance depends heavily on hyperparameters. So the important parameters here is learning rate, which means the effect of it is stability of training. Batch size is for gradient equality or quality. Batch size is for gradient quality. And epochs for training duration. Optimizer, its effect is convergence behavior. So the learning rate tuning, if the learning rate is too small, low learning. If it is too big, it's unstable. Why accuracy is not enough? We should use precision, recall, F1. Batch size affects training. So different batch sizes would become different results.